All right, I'm going over the 2.2 recommended assignment. There are 29 questions, so let's go over some of these. Question number 1. Sally takes the same bus to work every morning. The amount of time in minutes she has to wait for the bus can be modeled by a uniform distribution. Uniforms are flat across. So we're talking about, well, we got one that's flat across here, but you know that height is 1. So if you multiply 10 times 1, that's going to give you 10. This has to multiply to 1. That's not flat across. This is flat across, but this starts at 1, so that's only 9. This is flat across, and that's not. So it's going to be this one. And 10 times 0.1, that's 1. Question 2. Sally takes the same bus to work every morning. The amount of time in minutes that she has to wait for the bus can be modeled by the uniform distribution on the interval from 0 to 10 minutes. Same scenario, same height, same width. What percent of the days does Sally wait between 2.5 and 5.3 minutes? Well, 2.5 minutes would be the 25th percentile. 5.3 minutes would be the 53rd percentile. So you want to subtract those two numbers. So 53 minus 25, that should be 28%. Right there. Let's check that out. Next question. Sally takes the same bus to work every morning. The amount of time in minutes she has to wait for the bus can be modeled by a uniform distribution, again from 0 to 10 minutes. 70th percentile out of 10 minutes, that should be 7 minutes. Okay, question 4. The figure displays the density curve that models the distribution of quantitative data. Identify the location of the mean and median by letter for the graph. Well, the median should split the data up in half. Now, the top of that hump there, don't be deceived. There's less than half of that data here. But if you look over there, because this is skewed to the right, the mean is going to be higher than the median. So the median should be B, and the mean should be C. Mean should be C because that's further to the right of the median. But the median is right about in the halfway point of all the data. So let's check that. Nice. All right, this is a bimodal, 2 humps. Let's see the mean and median. Well, the mean and median, this is still symmetric, so they should both be in the middle. So I'm going to go with that one. All right. The weights of 9-ounce bags, in particular potato chips, can be modeled by a Norman distribution with a mean of 9.12 ounces and a standard deviation of 0.05. Well, we have to have the middle number be the mean, so we don't want to pick that. 9.12 is your mean. So since the standard deviation is 0.05, we have to add 0.05 to going up and down. That's adding 0.1. That's not adding 0.05. That's not even close. 9.12 plus 9.17, or plus 0.05, 0.05 is really small, so that should be 0.17. It should be this one here. All right, mean and standard deviation of the normal density curve. Ooh, this one's a little tougher because it's not scaled, but you know the mean's going to be 10. Now we got 3 options for standard deviation. Standard deviation of 6. Let me annotate over this a little bit so it makes more sense. Standard deviation of 6. 1, 2, 3, 4, 5, 6. No way. All right, that's one standard deviation should be right around here. So if you go like 2 above and 2 below, that looks approximately where it goes. I think 3 is a little bit too much. So I'm going to stick with 2. That should be our answer. Sometimes I get these wrong just because it's like arbitrary, but I'm pretty sure it's going to be that one. All right. Let's see, the weights in 9-ounce bags of particular brand of potato chips are modeled by a normal distribution, mean of 9.12, standard deviation of 0.05. Using the empirical rule, what percent of bags weigh less than 9.02? Well, let's do a little bit of thinking here. So 9.02, that's 0.1. So that's actually 2 standard deviations below. So if you do the empirical rule, that's what they want you to do here. We're at 9.12, 9.02, 9.07. So I say less than. Well, remember this is 34, 13.5, 2.35, and then 0.15. So these two added up should give you the less than 9.02. So that should be 2.5%. 2.5%. Pretty sure that's that one. Nice. All right, we're getting there. We're getting there. About okay. Another empirical rule, same scenario. A bag that weighs 9.7 ounces is at about what percentile? Well, let's think about that empirical rule for a minute. You know, remember this is 9.12. That is the 50th percentile. That's right in the middle. So 9.07, that's 1 standard deviation below. So let's think about what the percentages were, right? This is 34%, 34%. So if that's at 50, this percentile would be 50 minus 34. And then that means that 16% of the data is lower than, or at there or lower. So that should be the 16th percentile. 16th percentile. All right, next question. Please pause for any of these videos and feel free to kind of try them on your own first. I know I'm going fast, but it's a lot of problems, so I got to make sure this video is not super long. The weights in 9-ounce bags of a particular brand of potato chips can be modeled by a normal distribution with a mean. Same scenario. About what percent of 9-ounce bags of this potato chips weigh less than the 9 ounces? So now we're going to start getting into now we're starting getting to the non-empirical rule, and honestly, I'm just going to show you on the calculator because this is how you're going to want to do it. You can use the table, but what you're going to do is get rid of that here. So you're going to go into, you can press second, and you're going to hit bars. You go down norm CDF. And I'll do this on the 83 and the 84. All right, let's start with the 84. So you're, since it's saying less than 9 ounces, less than 9 ounces, that means your upper would be 9. Your lower would be negative infinity. So you say negative 1, EE, that's second comma, you say 99. Negative infinity, and then 9. Your mean, you put that 9.12, and your standard deviation, 0.05. So this is going to tell you approximately the percent that is below 9 ounces. Now it's a really small percent, right? That's 0.819%, 0.82%. Here, you do the negative 1 second comma for that E. That's negative 1 times 10 to the 99th power. Really, really small or large negative number, okay? And you do comma, and then you do the 9. And then you do comma, and then you do your mean. And then finally one more comma, and you do your standard deviation and you close it up. And there's your percent, 0.8%. It's a very small number. I'll check that. And most of your data is going to be done with the calculator. Let's do this one. And I'm going to stick with the 84, but know that with the 83s, you're doing the same thing. You're just using commas instead of inputting it in the menu. All right, a study investigated about 3,000 meals ordered from Chipotle, or as my mom says, Chipotle, restaurants using the online site Grubhub. Researchers calculated the sodium content for each order based on Chipotle's published nutrition information. The distribution of sodium content is approximately normal, with a mean of 2,000 milligrams and standard deviation 500. So we're just going to answer the question. What percent of meals ordered exceeded the recommended daily allowance? All right, exceeded more than. So second bars, normal CDF. That means 2,400 is your lower bound, okay? Your lower bound. So you put 2,400 here. Exceeded means everything above it. Well, that's positive infinity. So that's positive 1, E99. That's mean. We were talking about 2,000 and standard deviation of 500. So this is the percent above 2,400. And that we're looking at about 21.2%, 21.18. So that should be your answer. All right, next question. Study investigated about 3,000 meals. Same scenario. What percent of the meals ordered contained between 1,200 and 1,800 milligrams? Again, you just go through it. This time you got a lower and an upper. So you do your lower as 1,200, your upper as 1,800. Same mean and standard deviation here. I say 28.97, so we'll bump that up to 29%. Okay, so just for z-scores here, you can click on here to get the table if you want. Table A is also bit.ly/AP stats formulas. This is not the table and how it looks in the AP exam. It's a little bit different. Same numbers, but we don't go out to -4. That's just ridiculous. So I wouldn't even bother with that. So you talk about z-scores. So you go to second vars, and when it's a z-score, when it says z is greater, you say that your lower bound is -1.66. Greater than is, that means the z is the lower end, that goes higher. So you say 1E99 for infinity. But with z-scores, your mean is 0 and standard deviation is 1. So that goes resets back to 0 and 1. You know, on here, if you do normal CDF and you do -1.66, 1E99, if you close it up and you don't put a mean and standard deviation in, it defaults to 0 and 1 anyway. So if it's just talking about z-scores, you're going to get that answer. So that's 95%, 95%. So kind of same principle here. You know, you're just going between numbers. Again, I'll just stick with the 84. But second vars, normal CDF, -1.66, upper bound 2.85. Now we don't have to go to the table and get the 2% and subtract them. We just get the lower and the upper. Z-scores, so mean and standard deviation of 0 and 1, 94.9%. All right, Mrs. Starnes enjoys doing Sudoku puzzles. The time she takes to complete an easy puzzle can be modeled by a normal distribution with the mean 5.3 and standard deviation 0.9. What proportion of the time does Mrs. Starnes find an easy Sudoku puzzle in less than 3 minutes? All right, less than 3 minutes. What are we talking about? We got, so we're going to do our, put it right in here. Second vars, normal CDF less than 3. So that means you want negative infinity up until 3. So negative 1 E99, upper being 3, and your mean is 5.3, and your standard deviation is 0.9. See how easy this is? You just type it in. So yeah, that's about 0.53%. So the closest one I got here is 0.52. At that point, it's pretty negligible, the difference. Okay, the next one. How often does it take Mrs. Starnes to more than 6 minutes? More than 6 minutes. So normal CDF. Lower being 6, upper being positive infinity. Same mean and standard deviation. And that's a little bit bigger percentage. That's 21.8%. Okay, between 6 and 8 minutes. Now we're going to put a lower and an upper. And 21.7%. Pretty close to the last one, but a bit different. All right, so now let's talk about percentiles. 20th percentile is at that number or below. Okay, so 20% of the people wherever are at whatever the answer choice is or below. I don't want to get used to using your answer choices to help you. We're going to do this the right way using inverse norm. So you go to second vars and go down to inverse norm. Oops, second vars. Sorry, let me get out of there. Second vars, inverse norm means to get a value from the percent. So the area is always going to be that or below. That's how percentiles work too. So you can put 0.2 for 20 percentile, change your mean to 5.3, and your standard deviation to 0.9. That's going to be 4.54. You can do it on here too. Remember, we have an inverse norm, second vars, third option, but you got to input with commas. So you'll do 0.2, comma 5.3, comma 0.9. Inverse norm gets the value, normal CDF gets the percentage. All right. 19. Dot plot shows the EPA highway gas mileage estimates in miles per gallon for a random sample of 21 model year 2018 midsize cars. Explain why the distribution of gas, highway gas mileage is not approximately normal. Well, I'm looking at it, seeing it's a little bit skewed to the right. I see some points over here. So let's take a look. Distribution of highway gas mileage is not approximately normal because the distribution is skewed to the right. Let's look at our other options. There appears to be an outlier. Well, sure, but that doesn't make it necessarily not normal. Too much variability. This one says that is normal. This one says skew to the left. So I'm thinking, there is an outlier potentially, but these two don't necessarily, these still skew it a little bit. I would say skew to the right. Yeah, that was a little bit tricky. All right, let's this one. We're not going to enter all that in. Distribution of refrigerator capacity is approximately normal. Well, it's fairly symmetric. Let's look at the mean and median. The mean and median are a little bit off. So I'm not convinced they are normal, but they're not that far off. So this one's kind of tough. It's kind of tricky. I would lean toward it being normal, but I wouldn't say because it has a single peak. I mean, you could have a peak and then it'd be really flat on the outside, but it has a nice symmetric shape to it. So I'm likely to pick this one. So let's take a look. Let's see why I'm wrong. I'm get that wrong once in a while. So let's look at the clue. It says the alone is not enough to state that the distribution is approximately normal. Find the proportion of observations that are 1, 2, and 3 standard deviations from the mean. So let's take a look at what the standard deviation is. Standard deviation is about 1.2. So I'm just going to do a little calculator work here. If I look at the mean being 15.825, and I subtract 1.217 from that, then about 14.6. So right there, a little bit more than halfway to 15.825, so almost 16. We would want that to be roughly 34% of the data. And if I do 15.825 plus 1.217, I want to go to about 17.042. So let's just take a look at one standard deviation out. So I don't know, this is 10, and let's say this is 6, but we don't know, maybe half of them are through there. We could divvy it up if we wanted to and look over here how many there are. But let's look at the numbers here. So we got, this one's a little tough, 14.6, 17.042. So 14.6, I got 1, 2, 3. No, they're not going in order, of course. So we want to go to 15.8, 4, 5, 6, 7, 8. So it looks like I got 8 out of 36. Now, 8 out of 36, that's like 22%. That's not 34%. So I'm thinking one standard deviation below, I'm only getting 22%. Let's go above. So between 15.825 and 17.042, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 out of 36. Yikes. Look at that discrepancy, right? That's about 39%. So it does have some symmetry, but there's a little bit less going on here than there is here, right? So I think my thought process for just looking at the symmetry is not quite where it needs to be. I would not say it's normal. It's not approximately normal. So let's try that again. Well, I stand corrected. Apparently, it's going to be the empirical rule, even though I'm not quite there with it. But we'll move on. We make mistakes. Let's look at number 21. We collected data on the tuition charged by colleges and universities in Michigan. Hey, I'm from Michigan. Here's some numerical summaries for the data. Based on the relationship between the mean, standard deviation, minimum, and maximum, is it reasonable to believe that the distribution of Michigan's tuition is approximately normal? Well, mean, standard deviation, minimum, and maximum. Let's do a little bit of 10, 6, 1, 4. Let's do some adding. If I add 8049, I get 18,863. If I subtract it, I get 2,565. That's a huge standard deviation. Now look at that. Your min is if I take another 8,000 away from that, I'm in the negatives. Now, if I add 8,049 two times, I'm almost at the max. So this isn't going to be normal. Now, at the minimum, I would say the standard deviation is way too big. You know, it's just counting out. It's not, the data is too condensed in there. So that's going to be my answer. Well, I'm getting these wrong. Okay, well, the minimum's obviously closer to the mean than the maximum, so let's pick that. I don't like these questions, man. All right, this is a normal probability plot. What shape of the distribution is it? Well, let's just take a look here. It's approximately linear. There's a little bit of a dip there, so I would say it's approximately normal based off that somewhat linear approach. All right, question number 23. This is a normal probability plot. For it to be considered normal, of course, it would have to be somewhat linear, which it's not even close. But we do have what's going on is a lot of this stuff here. If you were to just focus on this position, and if these weren't here, you know, it might be considered linear. But guess what? This is pulling all that to the right, right? You got all these extreme values, especially this huge outlier here around 600. So it's going to be skewed to the right, big time, big time. Okay, two measures of center are marked on the density curve shown. The median is the yellow line, the mean is the red line. Well, first of all, if it's skewed to the right, the mean will be higher than the median. So let's get that out of there. The mean should be higher than the median. The median is at the red line, the mean's at the yellow line. We don't know what the mode is. So the median is going to be here, and the mean will be higher. All right, 25. Okay, weights of laboratory cockroaches can be modeled with the normal distribution have a mean of 80 grams and standard deviation of 2 grams. The following figure is the normal curve for the distribution of weights. All right, point C on this interval curve represents, well, the mean is 80, standard deviation is 2, this is 80, that's 2 less, let's say it's 78. All right, 26, same scenario. What percent of cockroaches have weights between 76 and 84? Well, let's see, 80, 78, 76. So 76, 80, 82, 84. That's 2 standard deviations away. That's your good old 95. 68, 95, 99.7. All right, what proportion of cockroaches will have weights greater than 83? Well, we don't have, I mean, we can guess with the empirical rule, but remember this is 80, 82. Greater than 82 would be 16%. So we know it's got to be less than 16%. 83 is pretty close, right? So I wouldn't say it's like 2%. It's definitely not 93%. Even these are pretty off. I mean, it's close to 83, but if we want to double check that, honestly, just use normal CDF. I don't see why we would guess on a problem like that. Second vars, normal CDF, greater than 83, so we're going to start with 83, upper 1E99, mean 80, standard deviation of 2. And it's a good thing we did that, right? Because I was thinking it would be this, but I was off. Check that out. So it's going to be 0.668. So that really you got to think about it, 83. And what I failed to recognize was this is 84. So that's actually halfway between it. So looks can be deceiving. That's why we use our calculator. Sometimes our estimates fail us. Let's check our answer. I swear. What percent of cockroaches have weights greater than 83 grams? All right, y'all. I think there's a typo on this one, so I do apologize. That's why we always check our work. But as you can see here, if I do 83 there, I did it twice, I'm getting 0.0668. It's saying it's wrong. If I do 82, it's saying 0.1586. Wait a minute. I thought I picked that first. I probably just clicked the wrong thing. Oh, God. It's too late. All right, different species of cockroach has weights that are approximately normally distributed with a mean of 50 grams. After measuring the weights of many of these cockroaches, the lab assistant reports that 14% of the cockroaches weigh more than 55. Based on this report, what is the approximate standard deviation of weight from the species of cockroaches? All right, let's just think about this for a minute. We haven't done a problem like this as an example. So let's think back to z-scores for a second. First, 14% weigh more than 55 grams. So I don't know the standard deviation. So we have to do z-score stuff first, okay? Let's pretend is, our percentile more than 14%. That's going to be somewhere over here. What is z when that proportion is at the at 14% or more in there, which means that that's going to be 1 minus 0.14. That's going to be 0.86. So the 86th percentile, more than 14%. So I want to know, what is z at the 86th percentile? So we will use the calculator for a little bit of it, but we do have to do some work. So what we do is we do second vars, inverse norm. We do 0.86. Leave that at 0 and 1 because we don't know the standard deviation, so we can't go messing with that yet. Now we know that z-score is 1.08. So what we're going to do is we're going to do a little algebra. Z is 1.08. We got z. So remember, z is the value minus the mean over the standard deviation. Well, we know the value, right? We know the value is 55. So if that's 1.08, that's your x value. Mean is 50. We just don't know that. So let's do a little bit of solving. Multiply this up here. So this times 1.08 equals 5. And then we can divide by 1.08. So your standard deviation will be whatever 5 divided by 1.08 is. So it's going to be, let's see. About 4.63. So we can get that. We can get that, 4.63. And our last question. Thank you for sticking with me. I know this was a little bit difficult for y'all, but hold on a second. I gotta. All right, I'm back. So looking at this data here, it is not a line, so it's not going to be normal. We got these extreme point. Most of your data is over here on the left side, but you got these extreme points on the right. So it's not going to be skewed left. It's going to be skewed right because of those points there. Straight line would be normal. All right, let's check that. Oh, how about I actually check it? Okay. Anyway, sorry about messing up those 3 problems, but hopefully this helps you. And I know it's a long video, but appreciate you watching to the end.